Hello, this is Kevin Bishop, and this is a presentation on distributed index construction using a Raspberry Pi cluster. And this is for the information retrieval course at Johns Hopkins University. Before I begin, I wanted to review the contents. So we'll begin with background and overview. We'll talk about the motivation for this problem, some common approaches to solve it. Then we'll go into project details of my particular project. In particular, we'll go over the hardware, then the software, and then finally the data sets that I used. And then we'll go into results, starting out with some observations that I made during the development process, and then we'll end with empirical results. Okay, starting with the background and overview. So what is the motivation for this? Why do we want to do distributed indexing? Well, it basically comes down to two things, size and speed. Modern data sets are simply too large to fit on even multi-terabyte machines. So you basically have to split it in terms of memory and even disk space, frankly, over multiple machines. And then secondly, even if you could fit it into memory, a single processor would just take far too long to handle something, for instance, like the size of the internet. And so the solution is cluster computing, which is to use a large number of machines working together cooperatively. So there are some difficulties with doing this. First, it's just the complexity. Managing a single process and a single machine is much simpler than multiple. There's no coordination involved across different machines. And then secondly, beyond just the complexity is also sublinear speed up. So it might be tempting to think if you have twice as many machines, you'll have twice the speed, 10 times as many machines, 10 times the speed. But that's not true. Partly because some problems are inherently serial. You can't split them up. And then also there are network communication latencies, and then also there's additional coordination processes. There are basically two overall approaches in terms of creating an index in a distributed fashion. First is to partition by document. So in that case, each node in the cluster is in charge of a subsection of the documents in the corpus. Another method is to partition by term. So in this case, each slave has, you can think of it as a section of the dictionary for which they are in charge. Okay, moving on to the project overview. So the goal of the project is twofold. First, I wanted to build a working distributed indexing system. And the reason for this is the basic concept of distributed computing is easy to grasp, but I wanted to actually build a working system and to learn the details. Much like we've done with many of our projects this semester, it's one thing to learn it in theory, but when you build it, you just learn it at a certain level of detail. And the second main goal is to evaluate the impact of cluster size on efficiency. So basically what I'm going to do is have small clusters, medium clusters, large clusters, and then measure the overall latency of the overall indexing process and various substeps. Okay, so as far as the hardware that I used, on the left you'll see a diagram, and basically what I have is 5 Raspberry Pis in a cluster, and they share a power source and they communicate via a network switch. Okay, there's a zoomed in image of the 5 Raspberry Pis sitting in their Lego server rack. And so each node is a Raspberry Pi 4B, and they have 2 gigabytes of RAM, 4 cores, a gigabit Ethernet, and then 16 gigabytes of storage on their SD cards. And then in terms of software, I use something called MPI, or Message Passing Interface Protocol. And it's a protocol that helps facilitate communication between master nodes and slave nodes. It just handles a lot of those low-level details. And then as far as the indexing code itself, I basically reused a lot of my TF-IDF projects. So the program flow is over on the right here. And basically how it works is the master node initially triggers off a job with n workers, 1 through 5. Then each of the nodes, the worker nodes, will loop over each batch, and they'll parse the documents, construct an index, save the partial index to disk, and then flush the postings lists from memory in order to save on RAM. Then once all of the partial indices are created, they merge them into one, and then they send their copy of the lexicon to the master. And then the master takes all these different lexicons and merges them and then distributes them into a kind of global dictionary. And then the nodes will take their local dictionaries and update it with the global inverse document frequency values. Because if you recall, that is necessary in order to compute the document lengths. And then finally, the master will merge all of the runtime statistics for the various nodes. So in terms of the data, I used the FIRE10 data set that was shared by Professor McNamee. And what I did was I split the corpus up into 100 batches of equal size. And the corpus size, there are 125,000 documents, and it's about a little over 300 megabytes. So I wanted to do a live demo real quick. So I've got a main bash script, and I pass the argument 5 to it to tell it that I want to run 5 nodes in the cluster. So here you can see that all of the Raspberry Pis, RPi00 through RPi04, they're all logging and giving information on how big their dictionaries are so far, how long it took to parse a single batch, and how long it took to construct an inverted file. So it takes several minutes to run, so I'm going to move on in the interest of time. So in terms of results, some observations I had from the development process. Overall, basically, working in a distributed environment is much more complex than working with one machine. In particular, it's pretty easy to overlook some details. For instance, one thing that caused me a headache quite a while was I didn't think about it, but term IDs are going to be different by node. So the different nodes are running into words in a different order. And if you recall, the term ID is basically just the order in which you ran into that word. So if you run into the word the first, that's going to be term ID 0. And so you basically can't merge or join the global dictionary on term ID. You have to join on term itself. Similarly, offsets are going to be different by nodes and also by partial index. And then another big one was coordinating the code. So in a single machine, you can just edit one file and then rerun it, and there's no need to do anything else. But in this case, you need a system in place to easily distribute and update the code. Okay, finally, I wanted to get into some empirical results. So the table on the left here is showing the size of the cluster on the different columns and then the various processors on the rows. And then on the right, we have a Gantt chart, which gives a little more detail. So you can see that the different worker nodes are all color coordinated. For instance, the master node is always yellow, and then worker node 01 is blue, worker node 02 is red, and so on. So at the bottom, we have the cluster when we have all 5 nodes working in it. And you can see that the latency, which is on the x-axis, is the smallest, like the total processing time. And then if you go up a bit, you have the cluster with 4 in it. And of course, as expected, the latency goes up. And then 3, it goes up more, 2, it goes up more, and then 1 is the longest. So next I wanted to go over how much did we reduce this. And in particular, I wanted to compare it to Amdahl's law, which is it shows the theoretical limit on how much you can improve something with parallelization. And I found something interesting. So according to this data, it's showing that the observed latency, the observed speedup, was faster than is what's theoretically possible. So I wanted to look into this, see what the cause is. So on the left here, we have the total speedup of the entire process. And then on the right, I have it split up by sub-process. And the blue line over here on the right is what's theoretical according to Amdahl's law, meaning if you have 2 nodes, it's twice as fast, 3 nodes is thrice as fast, and so on. And we still see many sub-processes are faster. So I decided to dig even further into this, and I had a suspicion that it might be the SD cards on the Raspberry Pis, because SD cards are notoriously slow for their I/O operations, and I thought maybe if too much load was being placed on a single machine, maybe it was causing outliers. And so that's what we're seeing here. I have the latency of disk-related operations versus memory-related operations on the y-axis. And the colors are the number, correspond to the number of nodes in the cluster size. And you can see all of these outliers off to the right here, and they're all shaded in light blue, which is indeed a one-node cluster. So this is at least strong evidence that there is something about the disk operations that's slowing this down. But basically, it's looking like it's pretty close to what's theoretically possible in terms of a speed up. All right, thank you very much. That's all I had to present. Hope you enjoyed.